today. And I'd like to introduce Alan Welk, whose course on is W2AEW. He is an RF application engineer for Tektronix, so he knows all about how to do testing of RF. It's been an interesting time for test equipment with the recent advances like the tiny SA and things like that. Revolutionised what I can do for testing. Now I'll hand over to Alan to give his presentation.
All right, thank you very much, Paul. Appreciate that. And let me do a share here and make sure this all works. Let me know if you guys can see a full screen.
Yeah, it looks good.
All right, beautiful. All right. So yeah, so let's dive right in here. Give you a little bit of an introduction here first. Again, I'm Alan Wilkie. I've been a field application engineer for Tektronix for a little over 15 years. And then before that, spent a little over 20 years as a design engineer, test engineer, application engineer for various companies working in various industries. But been working now for tech for like 15 years. It feels like about 3 because I've been having such a good time with it. But I'm a bit of a test equipment enthusiast. That's my basement lab, as you can see, and if you're familiar with my YouTube channel, you've seen maybe a couple of 100 videos filmed on that bench down there. So we're going to talk primarily about using RF test equipment, and for me, for the most part, that means primarily using spectrum analyzers, and it's something that was out of reach for a lot of people for a long time. Until things like the tiny SA and then like even the Rigol DSA 815 started to make some spectrum analyzers accessible to us mere mortals. So we'll talk a bit about spectrum analyzers and also spectrum analyzers that include tracking generators. And we'll also talk a bit about vector network analyzers. I was here last year and gave a talk on VNAs, so we'll cover a bit of that same topic, but so it might be a little bit repetitive for those that have seen the vector network analyzer talk before. We'll also talk a little bit about signal generators, and there's such a wide variety of them. I'm going to talk more about the different types that are out there and the good and bad things about each of those, rather than talking about how to use them so much. So a bit more of maybe a selection guide, so to speak. And we'll also even talk about using oscilloscopes. You might say, well, using oscilloscopes to look at RF, really? Well, yeah, really, you certainly can. And there's a couple of reasons to do that. So we'll talk about that as well. And then, of course, if you're going to use any type of equipment to take a look at what's going on with your signals, you want to know how to get those signals into the instrument and do it in a way that is non-invasive and non-disruptive as much as possible. And then we'll just cover a bit of a summary as we go along. I can't monitor the chat while we're talking here, so if some of the other panelists are monitoring the chat and an immediate question comes up, I'm happy to take it then. If not, we can certainly save questions till the end. So a little bit of an intro. So who's this for? Really for any of us, especially if you're doing any kind of building, home brewing, or testing of your equipment. And that could be anything from your antennas to building a kit or building some homebrew things, or if you need to do some minor repairs or something like that on RF equipment, or with your RF equipment. That's really what we're talking about here. And I'm going to really try to give you some practical hands-on tips, not complete tutorials, because just an hour isn't enough to give a tutorial on one piece of equipment, let alone several different types. So I'm really going to try to cover some of the practical hands-on tips and to help you understand the architecture, terminology, and controls on the instruments. I'm a firm believer of understanding the architecture of a piece of equipment or anything that you use. Understanding how it works makes you more efficient in using it properly. And that applies to a car with a manual transmission. If you understand how the clutch and transmission work, you can drive it better than if you don't know how it works, for example. Same thing holds true for electronic test equipment. So we're going to kind of cover some of that. And we'll talk about how to set them up properly to avoid getting improper results, because if you don't set them up properly, they're not going to tell you that. They're either going to lie to you or maybe do something more detrimental. So we'll try to learn how to set them up properly. And we'll talk about some typical use cases for the various pieces of equipment. So first, let's talk about spectrum analyzers. What are they? Okay, in its simplest form, it basically measures the amplitude of a signal, its power versus frequency. And in some sense, it's very similar to plotting your reading on your S meter as you tune across a frequency band. Now, of course, if a lot of you folks have probably got some SDR radios or even some of the more modern rigs that have got a waterfall display, well, that trace on the top of the waterfall display is essentially a spectrum analyzer. That's really what we're talking about. So quite simply, that's the primary function of what a spectrum analyzer is. And so in a sense, you could almost think of them as a swept-tuned receiver. In fact, the architecture of most, even especially the old school spectrum analyzers like these guys here, are really nothing more than a very sophisticated swept-tuned AM receiver. Okay, that's what it comes down to. But now some are also going to be either FFT or partially FFT based, meaning at some point the signal is getting sampled kind of like an oscilloscope, put into memory, and then the final result is then computed using a fast Fourier transform. At the end of the day, unless you're specifically using an FFT like on an oscilloscope, the fact that some of these instruments might be partially FFT based is kind of invisible to you. The Rigol is a good example of that. Even the tiny SA that's available now compute and display the results kind of at the end by doing at least an FFT at some point in the process. So let's look at the architecture, the guts, what's inside a spectrum analyzer. And this isn't quite the complete schematic or quite the complete block diagram, but if we take a look at it, we'll walk our way through here, this portion of the architecture first. We've got our RF input over here, okay? And the first thing generally that is available is in the instrument then is a variable RF attenuator, okay? And so that we can control how much power is going into the front end mixer. In many cases, not all cases, but in many cases, there will be some pre-selection filtering that goes ahead of the mixer. And this could be in the form of some block filters that get switched in depending on what frequency you're operating at. It could be just a low pass filter to kind of minimize the image generation out of the mixer. It might be a tracking bandpass filter or pre-selection filter that might be there. There's always at least one mixer, and generally there's going to be many more, a couple of more conversion stages in a real spectrum analyzer, but this is again a simplified block diagram. Okay. And again, the idea with the RF attenuator is to optimize the signal level into the mixer. You don't want it to be too small because you just suffer with your measurable signal to noise ratio, and you don't want it too big to so that to avoid damaging the mixer or generating unwanted intermodulation products. So the mixer is driven by a local oscillator, okay, and then the resulting IF signal goes through amplification and filtering stages, some kind of a detector of sorts, and maybe a filter after that, and then in an AM receiver, that would go off to an audio amplifier. So we've just described an AM receiver. So how is this different from a spectrum analyzer? Well, a spectrum analyzer adds a little ramp generator down here that drives and controls or sweeps the local oscillator. That same ramp generator also drives the sweep across the display. So what we can see is as we ramp up the voltage on the ramp generator, the frequency of the local oscillator is ramped up. Therefore, we're sweeping what input frequencies are landing in the IF and being detected and displayed. So as we sweep across the display from the ramp generator, we're plotting out amplitude of the various signals that are landing in the IF as we sweep across the band. So quite simply, that's what a kind of a typical old school swept spectrum analyzer does. Okay. We start talking about some analyzers that are partially FFT based. Oftentimes what that means is that the IF filter in these instruments are generally a little bit wider. And a digitizer is typically in this location here, and then the final result is computed by doing an FFT. So that's generally what you'll see, and that's similar to a software-defined radio. Oftentimes there will be some conversion into the digitizer, and then everything else is just done digitally from that point forward. And some modern spectrum analyzers work that way as well. So what's on the display of the spectrum analyzer? Okay, so obviously the x-axis down here, okay, the x-axis down here is frequency, okay, and it can either be shown as a center frequency and the span, or as a start and stop frequency typically, okay. The y-axis, the vertical axis, is calibrated in power, but generally, you're not going to see power in watts. We're going to talk about this a little bit later. You'll generally see power and most commonly in dBm. And we'll talk about why that is in a moment, and I'll give you a brief review of what dBm means. The reference level, another very important parameter with the spectrum analyzer, is the power level that is at the top of the display, this top line right along here. We can see this analyzer is set to a reference level of minus 30.72 dBm. And that represents the highest signal level that we can read on this display. But the other important thing, and I'll probably mention this a couple of times as we go through, setting that reference level is actually a pretty important thing, because what it does, if we go back to the block diagram, as you adjust the reference level, it adjusts the value of this RF attenuator, therefore adjusts the amount of signal that the front end mixer sees. So it tries to keep that in the optimum range. But it will also affect the vertical scale that you're going to get, and where the noise floor will be. Because as you might imagine, if the attenuator is set to 20 dB instead of 10 dB, the instrument's noise floor that shows up down here is going to be shown 10 dB higher, because the instrument is just going to say, okay, you've put 20 dB of attenuation in front of me. That means any signal that I'm going to show you is actually 20 dB higher. So I'm going to add 20 dB to all these numbers. Okay. And by doing that, now your noise floor is 20 dB higher, because we've essentially artificially added that number to it so that everything else is accurate. So you want to properly set the reference level so that the attenuator gets optimally low enough to give you the best signal to noise ratio. Okay. The resolution bandwidth is also shown. We see it says res bandwidth right down here. Okay. They're often called RBW, is what you'll hear me say, RBW, and just slip that in there. I'm talking about resolution bandwidth. And that's akin to the bandwidth that you might set your receiver to. Right, so you might have a filter, a filter set to 2.6 kilohertz or 2.4 kilohertz or 3 kilohertz for receiving single sideband. You might have a 400 hertz filter for CW, for example, to minimize the amount of noise you're receiving and to be able to, reject adjacent signals and things like that. That's exactly what resolution bandwidth is on a spectrum analyzer. Okay, we just call it resolution bandwidth instead of your IF filter. Also, we'll see VBW, that stands for video bandwidth. Video bandwidth is the post-detection filter, whereas the resolution bandwidth is the filter that's applied before the signal goes through the detector to detect its amplitude. After the detector, we just have a voltage level that represents the total amount of power detected in the RBW. That can also then be filtered, and that's called the video bandwidth. That's called VBW. And the effect of VBW is just to minimize the variation on the trace that you see here. It's not going to do much else than that, but it really tends to smooth the traces out. Okay, so the value of that will also be set. If the video bandwidth is set to the res bandwidth or higher, it's effectively off. It's not really doing anything. It's only when the video bandwidth is substantially narrower than the resolution bandwidth where you'll start to see its effect. Okay, and also the detector type. You can see up here, the detector type that's shown here is log power. And typically the detector type is going to be like an average detector, okay, or a sample detector, or maybe a positive peak detector are probably the most common ones that you'll use. And it's kind of like, it's almost like how your S meter is reading, right? It's how we're detecting power in that particular resolution bandwidth at that frequency to essentially give you a number that represents that power level at that given frequency. And of course, the sweep time will also be displayed down here. And that's how fast the analyzer is going to take to sweep from your start to your stop frequency. And then obviously the number of points is shown there as well. So on the amplitude units, as I mentioned, on a spectrum analyzer are usually in dBm, okay? And the reason for that is because this gives us the ability to view on the same display a very large range of signal levels. And another way to say that is a very wide dynamic range. So here's an example. Let's say we plotted amplitude in a linear scale like this. Excuse me. So let's say I had a milliwatt at one frequency, say right here. I'm losing my arrow, there it is. At a milliwatt, let me give myself a laser pointer here, might make it a little bit easier. So let's say I had a milliwatt signal at this frequency, let's say that we had frequency on this axis, and I had 50 milliwatts at this frequency. So that's a factor of 20 difference between those. And that's, you can see that's kind of, those two signals are kind of almost barely visible on that same scale, okay? And that's only a factor of 20, okay? If we convert these numbers to dBm, 1 milliwatt is 0 dBm, 50 microwatts is minus 13 dBm. If we plot them on a logarithmic scale, 0 dBm is right there, minus 13 dBm is right there. Gee, that's really easy to see. And look how much more I'd be able to see. I could see signals that are 30, 40, 50, 60 dB down. So a factor of 60, right? That's a factor of, you know, we'll say factor of 10 is 10 dB. Factor of 100 is 20 dB. Okay, a factor of 1,000 is 30 dB. 10,000 is 40 dB. So we can see a tremendous variation of signal levels when we use a logarithmic scale like dBm to display what we're going to look at on a spectrum analyzer. And that's typically why it's done. Now, oftentimes, if we're building, you know, a transmitter or something like that, we want to ensure that our harmonic generation or our spurious generation from the transmitter is 40 dB or more lower than the output power. Well, we wouldn't be able to see that on a linear scale. It just is a factor of 40 is a factor of 10,000 further down. You just wouldn't be able to see that on a linear scale. So you really have to use that logarithmic scale. Okay. So again, this is, and oftentimes when you see, you know, saying this term here, 40 dB down from something, that typically means 40 dB down from, say, a carrier level, and that's often expressed as 40 dBc, dB down from a carrier. So let's expand on this a little bit and talk about the basics of dBs. Okay, a dB without any kind of suffix on it is literally just a ratio between two numbers. It's like saying a factor of 10 or a factor of 32, okay, or twice as big or half as big. dB is just a ratio. It's not an absolute number. It's computed by this formula here. Just, you know, in the case of dB, we're talking about power levels. So we take the ratio of P2 to P1, right? This that fraction, but we're doing 10 times the log of that. And that's the definition of a dB. Okay. It's only when we add a suffix to the dB, like dBm or dBc, that it takes that ratio and we tell it what that ratio is now referenced to. Okay. So for example, a dBm means that we're referenced to a milliwatt, which means that P1 is a milliwatt. All right. So 0 dBm, because if we take the log of 1, the log of 1 is 0. Okay, so 10 times 0 is 0. Okay, so 0 dBm is a milliwatt of power. Okay, the 10 dBm is 10 milliwatts, 20 dBm is 100 milliwatts or 0.1 watts, 30 dBm is 1 watt, etc. Okay, by adding that suffix, we tell you what P2 or P1 is, and it turns the dB into an absolute value. The suffix doesn't always have to be M. Sometimes you will see other things like dBmV. That means that the suffix is now millivolts instead of milliwatts. And if we're going to compute in volts, we change the 10 to a 20. dBu, you'll see sometimes dB microvolts, dB milliamps, etc. Depending on what that suffix is, that tells you what that subscript is, or what the denominator is of that ratio. And again, the suffix turns dB into an absolute measurement. So instead of saying, hey, this is 10 times bigger, we can actually say this is 10 watts, okay, because it's an absolute measurement. So what is DBC? I kind of hinted at it on the previous slide. DBC still refers to a ratio between two power levels, except that the P1 becomes whatever the carrier power happens to be. Okay, so it's a relative measurement relative to the carrier power. Okay, but it's easy to measure on a spectrum analyzer, so we can put one marker on the carrier, put another marker on the signal that we're looking to measure, and the difference between those two is DBC. Okay, so if we have a signal level at 0 dBc, that means that that's the same power level as the carrier. Minus 20 dBc means that it's 1% of what the carrier power is. Okay, so again, the C turns it into, it's still an absolute number, but it's an absolute number reference to whatever the carrier power happens to be. So it's still a relative measurement. Okay, but it's a relative measurement that you can actually get a real power number on, an absolute number on if you want to, by knowing what the carrier power is. A couple of rules of thumb with dBs. When you're talking about power, each 3 dB change is either doubling or halving the power, right? If we increase by 3 dB, we're doubling power. If we decrease by 3 dB, we're halving power, okay? And then each 10 dB change is a 10 times change in power. So that one's easy to remember. Now, of course, since we know that power is equal to the square of voltage divided by impedance, for example, because of that square term, this 10 turns into a 20 if we need to compute that ratio in voltage. And therefore, these numbers kind of double. So a 6 dB change is doubling or halving the voltage. A 20 dB change is a 10x change in voltage. So those are your basic rules of thumb. Apologize for the word chart, here for the slide, but again, these slides will be made available to you, so you could always download this and keep this as a reference if you like. So on a spectrum analyzer, even though there's a lot of buttons on them typically, there's really only 4 main controls, and that's center frequency, span, resolution bandwidth, and reference level. Those are your 4 biggies, right, that you have on a spectrum analyzer. Okay, obviously the center frequency and span allow you to determine what range of frequencies do I want to measure. Okay, another way to kind of define that is by start and stop frequency. Okay, whichever is convenient for what you're trying to do. The resolution bandwidth selection, again, you're going to adjust this depending on how closely spaced are the frequencies that I need to measure. Like, do I need to see things that are 2 kilohertz apart? Or if I'm trying to look at like opposite sideband rejection on my transmitter, if it's a single sideband audio signal, you might want to have that resolution bandwidth set to something like 50 hertz or 100 hertz, so that the bandwidth of that filter can be more accurately show just the bandwidth of the signal, and you can see if that opposite sideband has gone away or not. If the resolution bandwidth is 10 kilohertz, the display is going to show, even for a pencil thin waveform, is going to show you a 10 kilohertz wide signal. So you really can't see how wide or narrow your signals are. So the resolution bandwidth has to be set to something narrower than the signal you want to measure, or narrower than the spacing of the signals that you need to see individually. I'll give you an example of that coming up here. And we talked a bit about reference level again. What's that highest power level that you're going to put into the analyzer at that point in time? Okay, you want the reference level to be equal to, or maybe even slightly higher than that highest power level that you're going to put in. Okay, and that's to ensure number one, you don't overload or damage the instrument, or that you have got sufficient signal above the noise floor to be able to see what you're trying to measure. So we want to set the frequency range. Typical screen on a spectrum analyzer might look like this. The center frequency is obviously the frequency at the center of the display horizontally. There's the center frequency setting. The span sets the total span around that center frequency and centered on that center frequency. Now, again, sometimes it's more convenient to, let me back up one, more convenient to set the start and stop frequency as opposed to setting the center frequency and span. And yeah, many analyzers will allow you to do that because that might be more convenient depending on what type of measurement you're making. So you can, generally the analyzers will allow you to pick and choose how you define the frequency range you're going to go measure. So let's talk a little bit about resolution bandwidth, okay? And we kind of talked about what it was. It's equivalent to like the IF filter in your radio. But let's look at the effect of that. So let's assume we have two sine waves at frequencies F1 and F2, okay? And their ideal representation would be, you know, say I got frequency going along the x-axis, power going this way. I've got an unmodulated signal, so I'm going to have some energy here and some energy here. Let's look at what happens if we try to look at this and plot it out on a spectrum analyzer using a wide resolution bandwidth. You can kind of picture the filter as a mask, right? And the detector is going to detect the total power in this white area, okay? So as we sweep this thing across those two frequencies, as those frequencies enter into the filter, they start adding up and being detected as power. And then as soon as they start leaving the open area there, the detection goes away. And now you're left with, well, we know those two signals we've got two signals with two individual power levels, but the spectrum analyzer is going to show that all as one large blob, okay? Because the resolution bandwidth was wider than the spacing of those two signals. So you don't get to see those individual results. Let's look at the same thing with a narrower resolution bandwidth, okay? Same two frequencies at F1 and F2. We now have a narrower filter. We're detecting power just over this narrow frequency range. So one effect of that is that at any point in time, the total random noise that we see is going to be less than the previous example because we're listening over a narrower bandwidth. Our eyes are narrowly focused. The same thing as switching in the CW filter and being able to dig out that CW signal from the noise or from surrounding neighbors. So let's look at what happens when we sweep this. Now, I purposely made this sweep slower because that's what happens in a spectrum analyzer. If you have the narrower you go in resolution bandwidth, the slower the sweep speed is going to be. But you'll notice now as we sweep through, only one of those signals lands in the filter at any given time. And we're now only going to, now we can individually resolve those two specific frequencies. All right. So, so why do we go slower? Well, there's two ways to think about this. The electronic way to think about it is that narrower filters have a longer time constant. And since they've got a longer time constant, you effectively have to dwell longer, you know, at any given point to allow that filter time to charge, and therefore to allow that filter to properly pass along the proper amplitude to the detector. Kind of the layman's way to think about this is picture yourself riding along the motorway. Okay, if you quickly glance around at all the cars surrounding you, it looks like you're all going the same speed. You're all kind of in a fixed position. You look around pretty quickly. But if you take the time to look at one car for a little bit longer, you'll see you can see how there's a slight difference. He's slightly pulling away from me, or I'm slightly catching up to him. But it takes that longer observation time to be able to resolve that small speed difference. The same thing happens electronically. If you want to resolve signals that are very closely spaced together, you have to have a longer observation time, a longer charge time to see that happen. Okay. So if we overlay these two traces from those results, this is exactly what we'd see, right? With the wide resolution bandwidth, you know, I see that wide thing and I can't see those two individual tones. The narrow resolution bandwidth gives me a lower noise floor, right? Because I'm detecting a less amount of power because of the narrower filter, even when I'm just detecting noise, and I can see those two signals resolve there, okay? So just as an example, here's the example of, say, a trace on a spectrum analyzer, just with no input connected. If you have a 10 kilohertz resolution bandwidth, the noise floor might be here. You reduce the resolution bandwidth to 1 kilohertz, that order of magnitude change in the filter also results in an order of magnitude or a 10 dB change in power. And therefore the noise floor goes down by 10 dB. You go down another order of magnitude, noise floor went down by another 10 dB. Okay, that's great. Why don't I always do that, right? The narrower resolution bandwidth gives you better frequency resolution and a lower noise floor, all good, but now at the expense of sweep time or processing time. So it's always a trade-off. You've got to decide, you know, how long am I willing to wait for this result? Okay, or, you know, versus, you know, what do I really need to see? So selecting that RBW is a bit of a trade-off. Okay, so And again, take a little bit closer look at the noise floor on the analyzer. Okay, what determines what that noise floor is? Obviously, each of the amplifiers and things like that have got a noise figure associated with them, and they generate their own noise and that type of thing. So, but what can you do? Because ideally, you want that noise floor to be as low as possible, so you can see very weak signals. Okay, so the displayed noise floor on a spectrum analyzer depends on, number one, the reference level. Okay, because again, that reference level sets that input attenuator. The input attenuator sets essentially how much I'm going to add to the measured result, okay, to give you an accurate power level reading. So the lower you can set the attenuator, the lower the numeric noise floor is going to be. It also affects the IF gain, therefore might also affect the noise figure of the IF stages as well. Okay, so ideally you want to set that reference level low. But as I mentioned, you also don't want to set it too low because you need to protect that mixer. And you also want to ensure that the mixer doesn't produce IMD or intermodulation distortion products. Okay, but so the reference level has a direct impact on noise floor because it sets the attenuator by default. Obviously, as we just discussed, the resolution bandwidth also affects the noise floor. Narrow RBW drops the noise floor down even more. So those two controls are the big contributing factors to what the noise floor in a spectrum analyzer will be. The detector type will have some effect, okay, as well as the video filter, because that kind of, again, affects the peak-to-peak amplitude of the trace itself, okay. So again, now you can, most spectrum analyzers go in and manually take control over that attenuator. Generally, by default, that input attenuator is tied to or coupled to the reference level. But once you've set that level, some analyzers will allow you to go in and say, well, let me take manual control over that because I think I know better than you, and then adjust it down even further. You can do that, but do that with caution. Again, because number one, you could start introducing distortion products that aren't really on your signal. Okay, that's probably the best thing you could do. The worst thing you could do is that you would expose that front end mixer to a damaging power level and damage the front end mixer of the analyzer, which can get very expensive. Okay. The resolution bandwidth, again, narrow RBW gives you that lower noise floor, but a slower sweep. So again, typically the resolution bandwidth or RBW is also coupled to the span. Okay. The wider the span, the wider the RBW. The narrower the span, the narrower the RBW. Okay. That's the way a spectrum analyzer works. It typically couples that RBW to the span. Because if I look at, say, a 10 megahertz span, I might have an RBW of 100 kilohertz or something. But if I go down to a 100 kilohertz span, the RBW might be 500 hertz, okay? Because I'm sweeping over a narrower range, you won't necessarily see the slower sweep because you're not going as far, okay? But if you want to do a wide span and a narrow RBW, that's the thing that can lead to really long sweep time. So again, it's something to just be careful of. The detector type and filter are not going to have a very dramatic effect on the noise floor, more just of the appearance of the noise floor, but not necessarily the absolute level of it. It's really the RBW reference level and really attenuator that determine what that noise floor is. So here's your kind of main operating tips to using a spectrum analyzer. One, most important, set that reference level just above the highest expected input power. If you're not sure, set it even higher. Okay, once you bring your signals on the analyzer, if your peak signal level is 20 dB below the reference level, then you can start knocking the reference level down. Okay, but it's always better to start high and work your way down. If you set the reference level too high, you're just going to have a poor signal to noise ratio because that signal is going to be kind of buried down in the noise because the higher the reference level, the higher the noise floor, and your signal level is just going to appear down, just barely peaking above the noise. So you don't want it to be too high, but again, too low, you can start getting distortion products generated by the mixer itself, or you could potentially do some damage to the mixer. Okay, so setting that reference level is probably one of the more important things to do. Another important thing is take a careful look at either the specifications or oftentimes the label on the front panel of the analyzer and respect that maximum allowable DC voltage rating. Now, sometimes, especially if we're probing or looking at RF signals inside of a circuit or directly at the output of an amplifier circuit that we're building, there may be some DC bias, on that signal. And some analyzers have a 0 volt maximum DC voltage rating, meaning that they don't want to see any DC content at all. Okay. In those cases, you might want to put a DC block or a coupling capacitor between the analyzer and what you're measuring. Okay. Some analyzers might be rated for 5 volts or 40 volts of maximum DC content on the signal, meaning that your RF signal has got some DC content that is riding on top of. But be sure to respect that, because not respecting that or violating that could also lead to an expensive day. And then, of course, set your frequency range either by center frequency and span or start and stop as needed. Okay. Leave the RBW auto coupled to the span until you know otherwise, right? So by generally the auto coupled RBW setting is going to be generally 0.1 to 1% of the span, and in most cases that's sufficient. But if you decide that, hey, I want something narrower, I can live with a slightly slower sweep speed, you can then uncouple them and adjust the RBW manually. And if you're going to do that, use the widest RBW that would give you the resolution you need. That's purely for speed reasons, right? If the measurement speed is not important to you, then you can go crazy and make that RBW as narrow as the analyzer will let you. Okay. And similarly, the sweep time is generally auto coupled to the span in RBW, specifically the RBW. And again, it's because that narrower filters have a longer time constant, so the sweep has to be slower. If you manually crank up the sweep speed and make it go faster, okay, then you're not going to give the detector time enough to see the full charge from the filter, and you're not going to get accurate results. Similarly, leave the input attenuator auto coupled to reference level until you have a reason not to, okay? And then if you're going to adjust it manually, do it very carefully. Generally, the only time you're going to do that is when you're looking at very weak signals, because many analyzers, even if you set the reference level to some very low level, minus 40, minus 50, minus 60 dBm, oftentimes that will leave, they'll have the attenuator set to some minimum value, maybe 10 dB. Okay, and that's to protect the mixer. But if you know, and you're comfortable with the fact that you're not going to put too much power in, you can then take that reference level manually down further, therefore dropping the noise level further, being able to see, you know, weaker and weaker signals. But it's something that you got to do with caution. But if you're not comfortable with that, just leave it on auto and set the reference level appropriately. Okay. So what are some common applications for a spectrum analyzer? Well, obviously one is looking at spectral purity or spectral content. Okay, maybe looking at harmonic content or spurious emissions. This is showing here a 1 gig span with a 50 kilohertz RBW. And I can see, you know, a signal here that's, you know, 75 dB down from this main signal that's right there. You might look at, you know, spectral content to how much your, you know, spectral width you're occupying. Occupied bandwidth, that can be measured a couple of ways if you're making an actual measurement. One is, you know, how wide do you have to go to encompass some percentage of the power, like 99% of the power is occupied, you know, within some bandwidth. Or another way to kind of specify it is what we call X dB down, saying that how far do you have to go on either side before the signal level drops X dB from the peak power. Okay, so that's called X dB down. Okay, so in this case, we could see that our 99% occupied bandwidth of this signal is 207 kilohertz, but the 26 dB down point is 224 kilohertz because we have to go down to about here, all right, 26 dB down. So it's a little bit wider because we're walking down the skirt of that signal. So it's another common measurement to make with a spectrum analyzer. Of course, spectrum monitoring, that's what the pan adapter is in your spectrum on your rig and your software-defined radios. That's purely just spectrum monitoring, and you get the benefit of a waterfall display and things like that to show the history of what was going on with the spectrum over time. Okay. And many spectrum analyzers give you the option to do what we call zero span, where if the span is set to 0, that means that you're setting a center frequency and not sweeping off that center frequency. So now you've turned it into an AM radio. Okay. And with that AM radio, you can plot out amplitude versus time to look at pulse signals, maybe CW pulses or something like that. But that's what zero span operation is. Okay. I think, now some spectrum analyzers give you the option of adding something called a tracking generator. So what is it? So here's our swept AM receiver, spectrum analyzer. A tracking generator, quite simply, takes that same ramp that's being used to sweep the frequencies that we're looking at and displaying, and uses that same ramp to drive a sweep oscillator, so that the tracking generator output frequency tracks the frequency we happen to be sweeping through at that instant in time. Okay, so this allows us now to apply a signal to a device we're testing to see how it responds, and then pick that up on the RF input. So if you, for example, if you put a bandpass filter here, all right, and you drive a signal into the bandpass filter, at some frequencies, the filter is going to not pass that signal, and other frequencies it is. And what you'll see on the display is the frequency response of that filter. Okay, it's kind of like a VNA, right, a vector network analyzer, except it doesn't give you any phase information. So it really is more of a scalar network analyzer function. Okay, so again, there's that one use right there. So here's our simplified spectrum analyzer and the tracking generator, and we've got our device under test. That device could be an amplifier, could be a filter, could be something, something like that. Could be a hunk of coax to look at loss to the coax over frequency, for example. So it could be anything that you want to check the frequency response of. Okay. Now, if you add a directional coupler or a return loss bridge, okay, to the generator output, and then connect your load up to that, like a return loss bridge, for example, or connect up the coupled signal to the analyzer, what you can then do is look at essentially the input reflection. Ideally, if you got a device that's perfectly impedance matched, all the energy coming out from the generator is going to go into the device, and then nothing is going to get reflected back, so you won't see anything. So you can use this to look at things like return loss, or even, in a sense, SWR, but you won't get a direct SWR reading. You're going to get a return loss or reflection coefficient measurement by doing this, but it gives you a way of looking at input match. Okay. Now, most tracking generators, when they're incorporated in there, will include a normalized function. Okay. So what that does is, let's say I wanted to test this filter out. The first thing you would do is, it's kind of like a calibration step. You would just simply connect the spectrum analyzer input to the tracking generator output, do the sweep over the frequency you have, and hit normalize. And what it'll do is it'll take whatever that trace is, okay, and flatten it out to be 0, saying that's my reference point. Okay. So then you open up the cables, stick your device under test, and you can measure just what your device is doing, ignoring the effect of any of the cables and connectors that you have. So that's what the normalized function will do. Now that's useful sometimes because oftentimes if you're measuring something that has got some kind of reflective properties, because for example, if you take that bandpass filter example, what happens when you're out of band? Does that filter absorb the signal, or does it reflect it? Okay, and many filters are not absorptive filters, they're reflective filters, meaning that outside of the band of interest, the reason the signal doesn't get through is because it gets reflected off the input back towards the tracking generator. That reflection can sometimes upset the tracking accuracy of a tracking generator. So oftentimes what you might do is stick maybe a 6 dB or 10 dB attenuator at the output of the tracking generator. That's going to make the signal that appears at the device 10 dB lower, but that doesn't matter generally. But it also ensures that even if the device is presenting a pretty bad mismatch to 50 ohms, the tracking generator is still going to see something pretty close to 50 ohms, so it's going to stay happy. So if you do a normalize with the attenuator in line, you'll essentially take the effect of that out of it, and then you can make your measurement result and not have any distortion or tracking problems due to the reflection of outside of band signals. Okay, so if you see sometimes people using a tracking generator with an attenuator, that's why. Okay, and the normalized function can help you essentially calibrate that out of the system. So with that, I'm going to switch gears a little bit here. Nick, I don't know, do we want to answer some questions that we have now up to this point, or do we want to just kind of go blast through to the end and do them all at the end?
Alan, if you want to take a break and get some questions now, I'm sure that people will be happy to do that. And
okay,
Paul, you're in the chair. Do you want to dive in and see if there's any questions?
Yeah, I just pulled the questions up here so I can see them. Okay. So yeah, so David's question: can you use an IC 7300 as a spectrum analyzer? In a sense, yes. but you want to be careful with that. I mean, it does have the spectrum display and the pan adapter. I don't have a 7300, so I don't know how adjustable that is in terms of a frequency range or span and how accurate it is. But if you're just looking at spectral content, that's essentially what the pan adapter is. But just have to be careful about how much power you put into it, because it's generally a radio receiver is not going to be designed to handle the higher level powers that a spectrum analyzer could. Okay. Dean asked, so if the Tiny SA has a minimum RBW of 2.4 kilohertz, it can't really be used at sideband suppression. And the answer to that, unfortunately, is correct. You can kind of get an idea, but it's not going to really give you the best view of it, because the minimum RBW is about as wide as your single sideband signal. So even if you had perfect, sideband suppression, it won't look perfect, because of the skirts of that filter kind of bleeding over to the other side of your carrier. Dave, N20A asks, or N20A asks, is there an advantage to using an external attenuator over the built-in attenuator on the spectrum analyzer? Not really, because when you use the internal attenuator, the analyzer will automatically account for that attenuator value, so your measured results on the screen will be accurate. The external attenuator, won't be accounted for. So you'd have to either account for it mentally or make an adjustment. Sometimes the analyzer can use an adjustment. So probably not an advantage to using that, other than what I just mentioned when it comes to the tracking generator. When you look at the DC level on an input, do you want to use a scope? Well, certainly you can. A scope could tell you what that DC level is, but then also, again, a coaxial DC block can also be used to kind of take that DC level out if there's any question. Okay. All right, so David decided one answer is no. Let's see, for an unknown signal level and or DC offset, is a blocking capacitor plus external attenuator a good protection method for an initial look? Absolutely. If you want to be absolutely safe, be sure you could certainly go ahead and do that. Are there other alternatives to avoiding destroying your analyzer? Again, it's really applying a lot of common sense, Chris, is just ensuring that take a look at settings that are in excess, like set that reference level really high, use an attenuator, look at your signal, say, okay, I'm 30 dB below my reference level. I'm okay to pull out this 10 dB attenuator, right? So just apply some common sense as you work your way through it, okay? And can the Tiny SA resolution bandwidth be set narrow enough to view suppressed carrier and both sidebands? Unfortunately, not really well, but that's what you get for $60. Okay. Johan, super, thank you. Any examples of when you use a different detector setting? Typically a positive peak or sample detector are what you want to use. If your signal has got if you're doing some modulation on the signal, sometimes a positive peak detect is what you want to see what the peak power is. If you got a lot of variation in noise floor and things like that, you might want to use an average detector, but it's oftentimes just to kind of give you what's going to be the most convenient for you. Let's see, how best to use when measuring cavities used with repeaters. If you're using a tracking generator with that, generally you can use a tracking generator to look at the reject characteristics pretty accurately. But when you want to look at the passband characteristics, it's best to use something like a return loss bridge or a directional coupler to look at the input return loss, because the passband characteristics are often soft enough that you can't find exactly where you're tuned to. But if you looked at the input reflection, that's going to give you a much sharper result at that tuned frequency for the passband. So you want to generally do that. Let's see, Peter says the noise floor is noted in dB per hertz. What does that mean? All that means is that it's power level with respect to a 1 hertz measurement bandwidth. Okay, so and in a rough sense, oftentimes an analyzer won't let you set the resolution bandwidth to 1 hertz. Okay, but it gives us a common point of reference amongst many manufacturers, because the minimum RBW you can set on a spectrum analyzer will vary by manufacturer. Not everyone can go down to a hertz. Not many can go down to a hertz. So they might go down to 100 hertz or 1 kilohertz or 300 hertz. So you can then convert that to a per hertz measurement so that everybody's on the same level playing field in terms of a spec. But so let's say the analyzer was spec'd for -150 dBm per hertz. Okay, if you had 100 hertz RBW, the noise floor would be 20 dB higher than that. Okay, so bandwidth of the scope, we're going to talk about scopes here in a bit. So hang on to that, Mike. Ron, is there a tracking generator essential for operation? Absolutely not. I mean, most spectrum analyzers don't have a tracking generator. And as Tony mentioned during his talk yesterday morning, oftentimes a broadband noise source can be used as a stimulus to a device and then use a spectrum analyzer at the output. Okay. For the Tiny SA, what range of attenuators we'd recommend? Unfortunately, John, I don't have direct experience with the Tiny SA. I don't have one, so I don't know what signal levels the Tiny SA is rated for. I would say probably 10, 20, 30 dBs are probably good ones to start with. Probably nothing less than 10, okay? Just to kind of put you in the right range. But again, I don't know what the reference level settings are and what the absolute max rating is of the Tiny SA. So maybe some others can chime in on the chat with that. What precautions do you take when checking harmonic levels from the transmitter? I'm going to talk about coupling signals in at the end of the talk here with things like RF samplers. So we'll deal with that when we talk about that. As a return loss detector or frequency sensitive, they can be, and that's why, again, a normalization function can help. Spot on what I was asking for you. Thank you. Let's see. Recommendations for an affordable spectrum analyzer for the amateur. The Rigel DSA 815 is like a $1,500 US unit. It's actually pretty good. I know there are less expensive units out there. I just don't have the direct experience with them to be able to recommend them, yay or nay. But if you want to get in really cheap, the Tiny SA gets you 80% of the way there for less than $100 US. As processing power gets cheaper, will analyzers move to more real-time analyzer designs? Absolutely, and we're seeing that as well in the professional world. So, all right, thank you for those questions. We'll move on, and if any more come up, just pop them in there, and we'll deal with them as we go on here. So, all right, so let's talk about VNAs. So I don't know how many of you were attended my VNA presentation last year, but this is a little bit of a rehash, but not entirely. Okay, so what is a VNA? Well, the VNA is essentially a device that can look at the reflection properties or transmission properties of a device. Okay, it can range from very inexpensive, okay, like the nano VNA that we've talked about, to very expensive, to well over several $100,000. And they're used to characterize devices for things like SWR, return loss, reflection coefficient, transmission gain and loss versus frequency. So the same kind of things we were just talking about with a tracking generator on a spectrum analyzer. The difference is with a VNA, the V stands for vector, which means it not only measures the amplitude of the return loss, reflection coefficient, transmission, et cetera, versus frequency, but it also measures the phase. Okay, if you don't, generally, why do we need to know that? We generally only need to know the phase when we're actually need to design things like matching networks and things like that. If you only care about the shape of the response curve, then the vector part of a VNA you don't really need. You don't need to know the phase. Okay, so a tracking generator on a spectrum analyzer oftentimes will do what you want as opposed to a VNA. Okay, so it can also look at things like complex impedance and obviously much more. Okay. So again, here's my simplified VNA diagram from my previous talk here. So we've got an RF source, which is a sweeping source, kind of like a tracking generator on a spectrum analyzer, that sends out a signal to our device under test through, in this case, port 1. We have a set of directional couplers that pick off and measure the amount of signal being sent and the amount of signal being reflected back from our DUT, okay? And we call those receivers, okay? So we'll call it R receiver, which is our reference receiver, okay? So that's our reference of how much signal we're sending out. Then we have an A and a B receiver, which measure the return signal from the input port of the device, so the reflected signal is in the A, and then the transmitted signal through the device under test is measured in the B receiver. And they measure both the magnitude and phase. Unlike a spectrum analyzer, which only measures magnitude in effectively this B receiver, unless you're using some kind of a return loss bridge to measure it the other way. Okay. Then obviously all the results from these receivers are all collected and computed to display the results. Our port 2 measurements are to measure gain and loss, just like we can do with a tracking generator and a spec-an. S21 is the complex transmission coefficient, so it includes the magnitude and phase. So that's called the transmission coefficient. You could also measure the insertion phase or the group delay of a device. And then on port 1, the signal's being reflected back off of the input. that's related to, we can compute SWR, we can compute reflection coefficient or S11. And also we can then compute return loss as well as the complex input impedance. Now, most professional VNAs will have these source, receivers, and coupler on both sides so that we can do not only S11, but S22, and then do transmission measurements in both directions as well. The nano VNA only has them on one side. Okay, so again, a brief review of what are S parameters. They're called scattering parameters. Does that clear it up for everybody? No, it doesn't for me either. So what it really is, it's simply a ratio of a measured response on port, the red port here, to the stimulus being applied from the Y port, okay? So it's a response measured on port X, resulting from a stimulus applied from port, I should say from port Y, okay? So, so in a sense, S11 is, when you think about those receivers, it's the result in the A receiver divided by the R receiver, okay? Because I got a signal being applied, being measured by the R receiver. I got a reflection going back, being measured by the A receiver. That ratio is the reflection from the DUT port, that's S11, okay? Measured on port 1 from the signal supplied by port 1, okay? S21 is the signal measured at port 2 from our reference signal being applied from port 1. Okay, so that's why it's called S21. Okay. So let's leave that there for a sec, just to be sure that everybody's got that. If you have any questions, again, type them in. But that's basically what S parameters are. The magnitude of S11 is essentially just our input reflection, and it's the inverse of return loss. Okay, return loss is generally a positive number. The reflection coefficient is a negative number. You just change the sign, and it's essentially the difference between the two. The frequency response, say, of a filter like we did with the tracking generator, is simply the magnitude of S21. Okay. So the other interesting thing with VNAs is that, why do I have to calibrate a VNA? I just got this VNA. Why do I have to calibrate it? Why don't I, what's the deal there? Well, why do we have to do that? One, we're measuring a very large dynamic range. So any small little errors, leakage paths and things like that, reflection paths and things like that, we want to account for to take them out, those kind of systematic errors, and get rid of them. And more importantly, since we're measuring phase is really another way of just talking about delay, right? So the amount of cables that you're connecting up to your device are going to introduce a delay, right? Because there's a propagation delay across that cable, which means it changes the phase of the signal that appears at your device. So if you want to see the actual phase response of your device, you got to be able to remove the phase of the interconnect out. And that's another thing that the user calibration does. And that's called establishing a measurement plane at the device that you're measuring. Okay. And obviously a factory calibration can't account for these things because a lot of those are dependent on how you're setting things up. Okay. So you want to do a calibration whenever you do a configuration change. You change cables, different lengths, different adapters, different fixtures, and obviously anytime you change the frequency range you're measuring is when you do the calibration. Okay, so it's really a calibration to zero out and remove all those things that the factory can't predict what you're going to do. All right, so a little bit of the calibration details. It corrects what we call these systematic errors. Tracking errors are the frequency response of the source and the A and B, and the source A and B receivers. So the tracking, those are tracking errors that get removed. There's matching errors that get removed. But if the ports aren't perfectly matched in impedance, you could get some reflections just due to the device or the instrument itself. So the matching errors will get reduced by doing the calibration. And also leakage paths such as between port 1 and port 2, signal that's going around your device. You want to account for that so that you can actually measure what your device is doing, as well as the imperfections of the directional couplers, the directivity of those couplers. Okay, and then obviously then the phase and attenuation results or properties of the interconnect cables to your DUT can be corrected as well. So the process is typically menu driven. It's a simple thing to go through, and it simply walks you through connecting various calibration standards in place of your DUT, an open, a short, a load, and a through. And then by taking these known devices, it can then compute what all these errors are and then mathematically remove them from your results. Okay, so what are the most common VNA measurements and formats? Okay, most measurements on a VN are made versus frequency. Okay, and the reflection coefficient, or S11, typically is going to be plotted in a log magnitude response. Okay, again, because we get some pretty sharp responses there, and a wide dynamic range. We typically use a logarithmic response there. And in this case, the lower, the greater the negative number, the more negative you go, the less reflection you have. Okay, return loss is just, you just take that the magnitude value and you remove the negative sign, and that's actually the definition of return loss. Some people still call return loss the negative number. It's just one of those things. So don't be afraid if you see a positive or negative return loss. We're still talking about the same thing, but strictly speaking, the definition is that the reflection coefficient, or S11, is a negative number, and the return loss is a positive number. That could also mathematically be converted into SWR. When we plot SWR on a VNA, it's typically done in a linear way to kind of show the ratio, like 2 to 1, 1.5 to 1, etc. It's generally done in a linear way. In general, it's going to be a softer curve than the S11 curve. Okay, even though my plots show it the other way around. Sorry about that. Also, you can look at complex impedance. Oftentimes, you'll use the Smith chart to measure complex impedance. It will also show you that it also shows you the complex reflection coefficient, but also is often used just to show complex impedance. Okay. And again, we refer to some of my VNA videos to talk about, I go into the Smith chart in great detail. The transmission coefficient, right? The frequency response of going through a device. For example, this is now looking at the frequency response, magnitude response of a bandpass filter. And this is looking at the S11, or the input return loss, input reflection coefficient of that same filter. So we can see that this filter is, in the passband, the S11 is a large negative number, which means it's got very little reflection, okay, in that passband. So it's going to pass the signal right through. But the way that this is actually being a bandpass filter is that for signals outside of the passband characteristic here and here, we can see that S11 is near 0 dB, which means it's reflecting all the signal back off of the port, back towards the source. That's why it's being a filter. It's rejecting the signal, not letting it through. It's not absorbing it. It's just sending it back where it came from. Okay, that's what that means. Okay. And of course, if you also can measure things like delay, insertion phase, group delay, they're generally going to be on a linear scale. Okay, but the S11, S21 are generally going to be displayed on a logarithmic magnitude scale. So the basic setup of a VNA, you're generally going to configure what traces and formats that you want to have, and set up the test frequency range. Similar to a spectrum analyzer, you set up a center frequency and span, or a start and stop frequency. Those can be interchanged in whichever way you want to go. Once you've determined those things, then you want to run through the calibration process for that particular analyzer. Okay, and then you would save and then apply those corrections to your test. Then you can connect up your DUT and make your tests, use your markers, adjust traces and formats as needed, and make all the measurements that you want. I put this together for the Nano VNA. That holds true for a $50 Nano VNA and a several $100,000 professional multi-port VNA. So that's the same process. All right, so with that, maybe we'll take another quick little break, take a look and see if there's any new questions that popped up in the Q&A, and then we'll dig into the next part of the talk here. So for the extra cost, Mike asks, do we go straight for a 2-port VNA? Well, most VNA, like anything that's labeled as a VNA, will often be a 2-port VNA, but it may not be a 2-port 2-path VNA. Meaning it may not have the source on both sides, and that's not absolutely necessary. A 2-port 1-path VNA, like a Nano VNA, will work very well. Some analyzers, like the rig experts and things like that, have basically got a single-port VNA capability, Okay, meaning that but they can only measure reflection properties, not transmission properties through a device. If you only need to measure input impedance, okay, like or SWR of an antenna system or something like that, then a single port VNA or like a typical antenna analyzer is all you really need. So, okay, Ron asks, in general, which is more useful to us radioamateurs, the VNA or the SpecAn? I would say, if you're a builder and experimenter, then probably the VNA, because if you need to often compute impedance matching networks and things like that, then the VNA is more useful. If you're primarily looking at just like spectral purity of an oscillator or harmonic content of a PA that you designed or something like that, then the spectrum analyzer is needed. But it really comes down to the type of work that you're doing. Really, almost either one of them could be, more important depending on what you're doing. But since they're both available for, the tiny SA and the nano VNAs are so inexpensive that you could have one of each of those. And then if you decide, hey, I need really better performance on the VNA because of the work I'm doing, then you can step up to, a bit more of an expensive instrument on that side, for example. So John, excuse me, hold on, Johan, just gotta take a drink. Johan asks, can one measure something containing a mixer with a VNA or nano VNA? Well, that would require generally an offset in the measure frequency versus the stimulus frequency. And the nano VNA, at least with the standard firmware it comes with, can't do that. There may be other firmware builds that allow that, but I don't think so, because I think from the architecture of the nano VNA, the mixers are all driven from the same RF source. So you can't have an offset between the received frequency and the transmitted frequency. As you step up to some of the more expensive VNAs, there are some that will give you the ability to do offset frequency measurements, which is what you need to measure like a frequency converting device, like a mixer. Unfortunately, the nano VNA can't, so as far as I know. So can I clarify what's meant by group delay and any other phase delay based measurement? So group delay can be thought of as kind of almost the physical delay in terms of time through a device, okay? Because if you have an amplifier, you send a signal in, it doesn't appear at the output instantaneously. There's going to be some small amount of delay there. And ideally that delay will be fixed. It might be, say a nanosecond of delay from the input to the output. And ideally that delay would be fixed whether you're putting in a megahertz or 10 megahertz, okay? The group delay measurement is a measurement of that delay versus frequency to see if it is indeed flat, okay? There are the filters and things like that oftentimes will not have a flat group delay, meaning that the delay through that device might be different in terms of time at different frequencies. It might delay higher frequencies more than lower frequencies. Sometimes that's intentional, sometimes it's an artifact of just the design. But the group delay plot is a measure of the delay through a device. It's measured in seconds, okay, or picoseconds or nanoseconds. Whereas a phase measurement, even if the delay is constant through a device, the phase measurement will vary with frequency, right? Because for a given delay, that represents a phase that will grow as the frequency gets higher, okay? So when you think of phase, if you get, sinusoidal signal that's traveling in time, right? As depending on how far you travel, that determines where you are from 0 to 360 degrees through the cycle, okay? So if you have a higher frequency signal, the same amount of time will be a larger phase. The group delay measurement takes the frequency portion and convolves that out of that, so you just get the raw delay number in time, okay? All right, so any recommendation for something better than the nano VNA that's still affordable below $1,000? Yeah, there's a couple out there. There's one called a Libra VNA, which is looking pretty good. It's still kind of one of these things that's still kind of under development, but it's got some pretty good performance parameters. I know there's some other like mini VNA and tiny VNA that have been developed. I've seen from places like Array Solutions and things like that have got things like that are available that are still under $1,000. So they're not bad to look at. I don't have any direct experience with them. I'm just kind of going by what I've seen out there. So, Alrighty, so I think we're good with those questions now. We'll move on to kind of the next part of the presentation here. Let's see, I'm just looking at time here, see what we're doing. I think we're doing okay. Okay, so signal generators for RF. It can take many forms, okay? So your proper, RF signal generators, like lab-based signal generators, like something like this, was it 8640? I can't remember the number of that, are out there. Of course, there's also kind of what I would call kind of service grade RF signal generators, like these guys here. You see the same exact generator with a dozen different manufacturers on it, but they're also quite usable. Also, function generators. Don't overlook function generators. They oftentimes can serve your RF needs pretty well, particularly at HF frequencies. So don't overlook that. And then there's a lot of what I would call kind of your non-traditional or maybe more non-professional signal generators. Things like, like this Feel Elec comes like out of Banggood, out of China. There's a couple of different models of these, and they're actually starting to get pretty good. Okay, still, and for about $100 is pretty amazing what you can get for that. But don't expect performance, that you would get on the professional units. But they're not bad to start looking at. But also, when I say non-traditional, the nano VNA, you might say, well, if I set the nano VNA span to 0, the output is just an RF output. Can I use that? Well, you can, but the output oftentimes, especially with the early nano VNAs, is actually a square wave. Okay, and you can't adjust the amplitude of it. Okay, even the tiny SA, one of its features is that it can be used as a signal generator. I don't know whether that signal generator output is either adjustable in amplitude, probably not, or probably not by much, or whether it's sinusoidal or a square wave. Okay, but they in a pinch, they could be used as signal generators. Not all spectrum analyzers are like that, but this tiny SA does have the function to be able to route its RF output or its local oscillator input to be an RF output. So let's take a look at some of the properties of these. So your proper signal generators are going to be very accurate in frequency, very low distortion, very low harmonic distortion, very low phase noise, a very wide output amplitude range. Okay, so you can adjust from well over 0 dBm to maybe 100, 120, 130 dB below 0 dBm, like minus 120, minus 130. Really useful if you want to look at receiver sensitivity measurements and minimum detectable signal type of things. Okay, or test a very low level amplifier. Okay, and they also will oftentimes have modulation capability. They're also, again, very, very stable. The downside is they could tend to be very expensive, even used several $100s for something like a typical lab grade, 40-year-old lab grade signal generator might still be several $100s. Now, these service signal generators are generally pretty inexpensive, and they're really easy to use. You pick a range, you dial the frequency in, okay? They're not going to be as precise in setting the frequency because you're just kind of looking at a vernier dial here. So you might need a frequency counter to actually measure the frequency if you need to be on something precise. And they're going to be, the output is not really perfectly sinusoidal. It's going to have some distortion to it. Just got to keep that in mind. Maybe have some type of limited modulation capability, maybe some, and the output amplitude range may be vernier adjustable, might just be adjustable over a certain range, not nearly as widely adjustable as a proper professional signal generator. Your function generators, generally pretty accurate in frequency. They're often direct digital synthesis type devices. They're pretty low distortion when it comes to the sinusoidal purity. They can also do things like frequency sweeps. They're going to be limited generally to HF frequencies or low HF frequencies and below, but they generally will work pretty well for that. And they've got other uses besides RF, because you can create square waves, triangle waves, pulses, and other things like that with a function generator. And they'll generally have a moderate output amplitude range. They probably won't be able to be adjustable to very, very low power levels, but they'll generally have a reasonably good output amplitude adjustable range. And usually some kind of modulation capability along with the sweep capability. When I say with the sweep capability, oftentimes I'll have a trigger output that you can actually do a sweep with the trigger output and then use your oscilloscope as opposed to a spectrum analyzer to sweep things like filters and things like that. Okay. Now, your non-traditional, non-professional generators, generally very inexpensive and easy to use. Again, just be careful, like things like the early nano VNAs that got a square wave output. okay, and sometimes don't have any adjustability on the output amplitude range or have a very limited output amplitude range adjustment. So you want to be sure that you know what the amplitude range is and think about that with respect to what you might need for the things that you're going to be testing. Sometimes we'll have limited or no modulation capability at all. Okay, so that's kind of where they all stand. Generally, if you get into something like this Feel-Elec, FY6900, it will have some modulation capability. I'm not sure if it does sweeps, but it probably does. Looks like it actually has 2 outputs, so you might be able to do some things interesting with that. So I don't have any direct experience with them, but they're out there, and they're, again, typically $100-ish type devices. So really kind of pretty amazing what you can get these days that you couldn't get even 5 years ago. So when you're talking about signal generators, there may be some accessories you want to go along with those, maybe to overcome some of the limitations of the devices. And the first and foremost might be attenuators. If you're using a function generator or one of these other generators that can't give you very low levels, and you want to do things like sensitivity measurements on a receiver, you might need a range of attenuators to bring the signal down low enough to be able to go do those measurements. And they could be either fixed or kind of step or variable attenuators. Okay, again, very helpful if you can't go low enough on your SIG-Gen. DC blocks, not so much because the signal generator is going to generally not have a DC offset, but you might try to couple into a circuit that's got some DC bias on it. So you might want to have a coaxial DC block, not only to use on the front end of your spectrum analyzer, but also to use to couple signals into your circuits without having the DC offset in your circuit back feed into your generator. Okay. So generators might have an AC coupling on the output, they might not. Bias tees, again, similar reason, they'll block the DC, but you could also use it to inject DC into your circuit, or maybe even monitor DC coming off of your circuit, so you can see what's going on. So the bias tees can be useful to have as well. And obviously filters, especially if you're using one of these generators that is not really clean or is a square wave output, having some filters, either passband filters or low pass filters or something adjustable, might help to clean that signal up to use for your purposes. So with that, let's see if there's any quick questions on SIG-Gens, and then we'll move on to scopes. Okay, so it was just following up on the group delay. It's kind of like, so ripple in a filter is often caused by nonlinearities in group delay, because if the various frequency components are going at different phases, then they'll add and subtract constructively or destructively. And that's often what leads to ripple. 8640B, that's right. Thanks, Mike. Okay, so let's close this. So let's talk about oscilloscopes for RF, really? Well, yeah, why not? Sure. Okay, so let's talk about there's analog types like the venerable Tech 465B, the very popular Rigol digital scope, the DS 1054 certainly can be used for RF if we do things right. What are some of the common tasks? Well, you can use it as an RF signal monitor. Here's kind of on an analog scope. Okay, here's what might look like on a digital scope. Okay, so coupling an RF signal in and monitoring your RF envelope is one way to use a scope. Obviously, if you're doing any kind of circuit building, okay, tracing your signals through, looking for signal clipping and distortion, just the typical uses for an oscilloscope. Oscilloscopes are available these days with really high frequencies. So certainly whether the signal is at RF frequencies or not, they can certainly still be used. Also, you can use them in XY mode to do like trapezoidal measurements for looking at amplifier linearity. We'll get into that. I don't have not get into exactly how you set that up in this talk here, but that's something you certainly can do, and it's certainly a use for oscilloscopes. Okay, so let's talk about our considerations for RF use, both analog and digital. We want to talk about bandwidth, right? Ideally, the oscilloscope bandwidth needs to exceed the RF signal frequency that you want to look at. Okay. Now, for accurate measurements, meaning less than 2% error in amplitude, the actual bandwidth of the scope should be about 5 times your RF signal frequency. Yikes, right? So if I want to look at a 20 megahertz signal, I need a 100 megahertz scope. Well, why is that? It's due to the roll-off of the frequency response of the scope. An oscilloscope's bandwidth is rated by its 3 dB bandwidth of the vertical response. Okay, so it might look like this. Okay, so if I've got a 100 megahertz scope, that's where it's 3 dB down. So if I put a 100 megahertz signal into the scope, it's going to read at 70% of its actual amplitude. So if I want the amplitude accuracy to be within 2%, I need to be at, ideally 5 times lower than the rated bandwidth. Now, some scopes have got a steeper than a single pole roll off like this, and you can get away with a little bit less than 5x, but that's really what it is. And this is very much unlike a spectrum analyzer or a VNA, where if you have a spectrum analyzer that says it's good to 1 gig, it's rated to measure out to 1 gig, but then it cuts off right there. Okay, a VNA is the same way. So they're rated out to the frequency range. An oscilloscope is rated by its 3 dB bandwidth. So you just have to keep that in mind. Okay. So if you're fine with relative measurements, amplitude measurements, rather than absolute measurements, then having a scope that's got, a bandwidth that's equal to or even less than the signal that you're interested in is fine, right? You could use a 10 megahertz scope as a RF signal monitor. Just crank the amplitude up when you get higher in frequency, right? If you're just looking at the relative amplitude, it doesn't matter, right? But if you want accurate measurements, that's where you got to worry about it. So let's talk about just some considerations just on the digital scope side. So some more considerations here. One is sample rate, okay? Sample rate has to be greater than 2.5 times your RF frequency. Now, Nyquist says it has to be greater than 2 times, right? But the problem with Nyquist is that with 2x sampling, two times the RF frequency, it means you're only grabbing 2 points with each RF cycle. You're not going to get anywhere near accurate amplitude measurements by doing that. So the general rule of thumb for RF is at least 2.5 times the RF frequency, and preferably more. And ideally, this is to prevent aliasing. Once you go down below 2, you can actually get aliasing. And this is what aliasing looks like. Let's say our red signal is our real signal that is going into the scope, but our sample rate is less than that frequency. That's our green dots. So we can see we one sample here, the next sample is here, the next sample is here. And if you connect those dots, they connect at a different frequency. So that's aliasing. And this is, I call that, it's like the wagon wheel effect. You watch the old Western movies on TV, right? And it's the horses are pulling those wagons. Sometimes it looks like those wagon wheels are slowly turning backwards. And that's because the frame rate of the film is catching the wheels at that portion of the rotation. Okay, but you're not capturing every spot in the rotation. So it can, the way it adds up, sometimes it can look like they're turning slower, turning faster, turning the opposite direction. That's the same thing as aliasing. So we need a high enough sample rate to prevent that when we're looking at high frequency signals like RF. Now, memory depth is important too. Well, why is that? Well, even if your scope has got a high sample rate, it might not always use it, right? Because it really depends on how you have the scope set up. At slow sweep speeds, meaning higher seconds per division, like if I'm looking at, instead of looking at, say, 10 microseconds across the width of the scope screen, I'm looking at 10 milliseconds, right? I can only display so many points, right? So what happens is that sample point resolution, you have to think about how many points can I fit in memory, okay, over a given amount of time, right? If that time is long, okay, if I want to have a very, very fine resolution, like 1 over the sample rate to be, again, my sample rate's got to be above my RF frequency. So I'm going to sample really fast. But if I want to have a long acquisition time, I need a lot of memory because I'm taking a lot of pictures of that waveform or that samples of that waveform over time. And I've got to have the memory to store that in. Because if I don't, then I'm going to alias, right? So the update rate, though, can suffer with deep memory. So it's one of the things to think about. Okay, I've got the high sample, I got the high memory, but now I've got so much data to process, it's not going to update very fast. And these are some of the problems with using a digital scope when it comes to RF. Now, the sample processing from memory to the display might need to be tweaked because I might set the memory, the waveform memory, to be like 1 million points, but the display, the LCD display on the scope screen isn't going to have 1 million pixels across it. So that some processing has to happen to take the waveform from memory to put it on the display. Hopefully, they're going to do something to process that data in a way that makes sense. Okay, so for example, I have all these sample points that you can see along here, but my display interval is much coarser. So ideally, maybe you take all those display points and you add them all up and kind of color grade their amplitudes to kind of get this color graded representation. That's kind of the best, almost not the best thing, but one of the better ways to kind of represent the compression of the actual waveform samples into the display. Some scopes will only take 1 sample out of each of these intervals. Okay, and then even though your sample rate was high, you're going to alias on the display. Some scopes will give you the way of adjusting what that display processing is. to do like a color graded, to do a min max hold, or do an average or something like that. So you might have to tweak that depending on how you set the scope up. So if you've got this intensity graded waveform display, that's kind of important for looking at doing like RF monitoring and that type of thing. Now, one of the big advantages of the digital scopes is that you can get basic spectrum analysis on a scope by using an FFT. So I've got samples collected over time, and doing this mathematical operation called fast Fourier transform, I can basically get the spectral content. I've got a whole video on this. I'm not going to go into the great detail, but the two things you can remember is that the frequency range of the FFT result is going to range from DC out to 1/2 of the sample rate. So if my sample rate is a gigahertz, then the frequency range is going to be from DC to 500 meg. If my sample rate is 200 megahertz, then it's going to be DC out to 100 meg. Okay. The frequency resolution, essentially the equivalent of RBW on the FFT, is generally proportional to 1 over the acquisition time, the total acquisition time that you acquired. So like your horizontal scale times 10, because you typically have 10 divisions across the screen. And if you're set to a millisecond a division, then you'd have 10 millisecond capture. 1 over that 10 milliseconds is essentially going to be the frequency resolution that you get out of the FFT. So those are your kind of two general rules of thumb. Some scopes will allow you to adjust that scale so you can zero in or zoom in on a certain portion of it, but the raw FFT function is going to be controlled by that. That's just the mathematics of it. All right, so let's take a look at analog CRT-based scopes for RF. They're really great for doing RF envelope monitoring, okay? Also they do XY mode really, really well, okay? For things like the trapezoid pattern and things like that. They're generally pretty easy to use, oftentimes, a knob per input and things like that. And the inputs are pretty well arranged. And I've got a ton of tutorials on my YouTube channel as well as how to use a scope if you don't know how. But they're really best for when your signals are continuous or always there, because there's no storage, okay? But not so good is that most analog scopes are pretty old these days, okay? And they might need fixing, okay? Some people like that, okay? It gives them something to do, but just keep that in mind. They're generally physically large, generally deep, because the CRT is pretty deep, so they take up a lot of bench space. And they don't have any storage. Most of them don't have any storage on them. Okay, so they're really only good for looking at live signals. Okay, but they get a nice live update rate. You turn the control, the changes happen immediately. Everything reacts immediately because it's all just being driven live. No memory, no processing. Okay, we did an awful lot with analog scopes for 50 years before digital scopes came along. So yeah, so you can do a lot with analog scopes. Okay. Again, not so great for bursty or transient signals because we only show what's going on live. Digital scopes, the good, really small footprint, especially the depth of them. You get automatic measurements, peak-to-peak measurements, frequency measurements, amplitude measurements. Automatically, you don't have to count divisions, so that's good stuff. You get some waveform capture and storage, so you can actually take pictures and document things and study what's going on, especially if you got like bursty or transient signals. And you have some advanced features like FFT to do spectrum analysis, all really good things. And not so good, you got those sample rate and memory concerns with aliasing, something you got to be aware of. If the scope happens to have an intensity graded display for looking at RF envelopes, that's pretty good, okay? They're not quite live update. Some scopes are more sluggish than others, so it's just something to keep in mind. When you compare it to an analog scope, it's going to be obvious, but if it's all you've ever used a digital scope, you might not notice it. And they're generally going to be more expensive, okay? But even like, I think this Rigol is a couple $100, so it's not really terrible. But those really cheap sub $100 ones that look kind of like the Nano VNA are not going to have the bandwidth to look at RF signals. They're really about good for audio, okay? And they really, unfortunately, have pretty lousy XY operation. So if you want to do anything with that XY operation, like for a trapezoid, the digital scopes are just kind of horrible at that. So let's talk about how to get signals into your instruments, right? So how do we get them into the instrument without, number one, damaging the instrument, or without distorting the RF signal or loading the circuit, okay? So we want to be careful about watching our signal levels, of course. And we also have to be careful about watching the impedances that we're dealing with in terms of probes and loads and things like that. So let's dig into this a little bit.
Alan, I'm sorry to chip in, but we're running out of time.
Okay.
Could you sort of wrap it up and
yeah, this I feel like I like 2 more slides, so I'll wrap up quick.
fantastic.
All right, great, thank you. All right, so probing signals. If you're inserting into a coaxial line, RF samplers are a nice way to go to kind of just sample a portion of the signal, and they're generally adjustable, so you can get a low-level signal going into a spectrum analyzer or scope. You can homebrew things. You can also use directional couplers like they're inside of a VNA, or even use power dividers and splitters when you don't necessarily need to attenuate the signal, dramatically. But these first guys will really attenuate the RF signal, so it's really good for looking at like transmitter outputs. Okay, if you're probing signals at the RF circuit level, Z0 probes are kind of nice. This P6150 from Tektronix looks like a 450 ohm resistor in series with the 50 ohm coax. So it gives you a 10x voltage divider and presents a 500 ohm load to the circuit, which for RF circuits is oftentimes okay. And you can homebrew something like that pretty easily. Near field probes can be used to probe around RF signals and bring them in a relative sense. You're not going to get anything calibrated out of them, but it's a way of just getting signals into, say, a spectrum analyzer. Or using a power detector just to look at RF amplitude. You can use that on a scope or even on a meter. You can get them coaxially, or you can go build something like this into a probe handle. Okay, and of course, oscilloscope 10x probes can be used. Just watch the capacitive loading and keep your leads short. So watch your impedances. Spectrum analyzers are generally 50 ohms. They're generally AC or DC coupled. They'll tell you what they are. VNAs are too. That works really well with the samplers and directional couplers and Z0 probes and the power dividers. Does not work with 10x probes or RF detectors. On the scopes, typically 1 mega ohm AC or DC coupled. Some have got a 50 ohms termination selection, some don't. Those you can use a 50 ohm through termination if you actually want to bring 50 ohms to the scope. But these work really well with 10x probes. Again, beware of the loading and keep your ground leads short. Also usable with samplers, couplers, and near field probes. Okay, so resources available to you. YouTube, shameless plug for my YouTube channel. You'll have a copy of this presentation, so there's some links to my video index as well as some relevant playlists for spectrum analyzers and ham radio and VNA related videos. So quick summary, don't be scared of spectrum analyzers, VNAs. They're not just for professionals anymore. Even scopes work for RF work. And then put some thought into sensing, probing, and connecting up your circuits. And lots of resources out there, not just my channel. So I think that's what I had. Apologize for running a couple of minutes late, but I'm the last guy, so I get a little bit of a pass. So anyway, with that, I don't know if it doesn't look like there was any new questions in the Q&A. I guess I'll stop sharing here. We can take a look at the chat and see if there's anything that came up in there that we might want to talk about. So
okay, thank you very much, Alan. That was incredibly interesting and useful. All sorts of new things to think about using my tiny essay. So I'll be looking into that.
Okay.
If there's any other questions, if there aren't any other questions, I'll close the meeting and then the next meeting will start, I expect. Thank you very much, everybody.